Alright, this is going to be our second lecture of Module 2. In this lecture, we're going to be going over conductor sizing and adjustment. And this is going to be in Article 310, which is going to start on page 144 of your 2017 NEC. So our objectives for this lesson, we're going to use Table 310.4a to identify conductor insulation types, list the requirements for conductors installed in parallel, make ambient temperature impacity adjustments per Table 310.15b1, make impacity adjustments for more than 3 current carrying conductors per Table 310.15c1, and use Table 310.15b16 to size conductor and copper and aluminum conductors. So definitions: with parallel, extending in the same direction everywhere or equidistant. For our purposes, you can essentially think of parallel installations where we're using 2 sets of circuit conductors for one circuit. And what I mean by that is if we take a standard 120 volt circuit where we have a ungrounded conductor and a grounded circuit conductor in a parallel circuit, we would be using 2 ungrounded conductors and 2 grounded conductors to supply that piece of equipment. Opacity, the maximum amount of current that a wire or cable can safely carry. Ambient, an encompassing atmosphere or environment. For our purposes, ambient, and we're going to be referring to ambient in terms of temperature. The ambient temperature of an area is what we would say that that area will normally be operating at. So if we think about, outdoors in Kentucky, we see temperatures all the way up to 90, even low hundreds during the summer, so that would be the maximum temperature we would have to look at there. Versus indoors, there's multiple factors that can affect that, such as is it climate controlled? Is there heavy equipment that produces heat operating in the area? So it really depends on where we're installing our conductors at is we're going to be looking at that ambient temperature and adjust to bring to a more satisfactory state. And we'll be getting into a little bit more about why and when we do impacity adjustments later in the lecture. So Article 310, conductors for general wiring. Article 310 covers the general requirements for conductors, and this does not apply to conductors integral to equipment. So in other words, anytime that we're talking about a conductor, unless it's integral to a piece of equipment, we're going to be referring in some way to Article 310. All conductors listed by code can be used in any dry location. It's kind of a quick little note to start off here. In other words, any type of circuit conductor, and typically when we're referring to any type of conductor, we're talking about different insulation types. Any insulation type on any wire is suitable for dry locations. Now, we do have specific requirements for conductors that can be used in damp and dry locations, which are covered in 310.10b, and then we also have additional requirements for conductors installed in wet locations, which are listed in 310.10c. So any conductor, once again, can be used in a dry location, but if we're going to be using them in a damp or a wet location, we need to verify in 310.10b and 310.10c whether we can use that type of conductor in that type of area. So looking at some specific conductor requirements, and for parallel conductors, circuit conductors 1 gauge and larger may be connected in parallel if installed per 310.10 H2 through 6. So I already told you all kind of what we'll be referring to when we're talking about installing conductors in parallel. So the important note here is we can only install circuit conductors 1 gauge and larger in parallel. In other words, if it's smaller than 1 gauge, we have to use a single set of circuit conductors. We can't make a parallel installation. And then they're required to meet all the requirements of 310.10 H2 through C. So we have multiple requirements if we're going to do a parallel installation. So H2 tells us that the conductors must be the same type, size, length, and terminated the same. In other words, if we're using THHN conductors, all the conductors installed in parallel have to be THHN. If we're installing 250 kc mil conductors, both sets of conductors have to be 250 kc mil. We can't make one of them be 4/0 and then use 250 kc mil for another one. They have to be the exact same length, so we can't make one of them be 25 feet and the other one be 30. They both have to be the same length. And then they have to be terminated the same way. So we can't use, crimp lugs for one of them and then factory bolt lugs for the other set of conductors. Whatever way we're terminating one set, they both have to be done the same way. H3, they must have the same characteristics, unless single phase. Once again, this is kind of just another note about the general type of conductor you're using. H4, they must comply with 310.15b3a. We'll be talking about 310.15b3a a little bit later in the lecture. And H5, grounding conductors must be sized per 250.122. This kind of goes back to our previous module where we talked about grounding and bonding. And finally, H6, a bonding jumper must be installed and sized per 250.102. Once again, this goes back to our previous module, grounding and bonding. So sticking with our conductor requirements, going to be taking a look at ampacities now. And this is going to be one of the bigger parts of Article 310 is conductor ampacities. Conductors cannot be installed in a way that exceeds the temperature rating of the insulation. And before I go into this, let's talk through another couple points here. Factors include ambient temperature, load current flow, rate at which heat dissipates ambiently, and adjacent load carrying conductors. So now we've kind of taken a look at some of these examples. The essential idea here is that when we install circuit conductors for a given circuit, if those conductors are only rated for 60 degrees Celsius, we don't want those conductors to ever be caused to get warmer than that 60 degrees Celsius rating that they're in. And then here we have some things that could cause that. If we put too much current flow on a conductor that's only rated for, say we're using a number 10 gauge wire at 60 degrees Celsius that's rated for 30 amps, if we put 40 amps on that conductor, it's going to cause it to heat up beyond 60 degrees Celsius, which is its given rating. If we install those 60 degrees Celsius conductors in an area that is ambiently 90 degrees Celsius, then they're going to heat up warmer than 60 degrees Celsius. And then for another example would be if we have 60 degrees Celsius conductors installed directly beside of 75 degrees Celsius conductors, there's the possibility that that warmer set of conductors could cause the 60 degrees Celsius conductors to heat up too much. Now obviously we don't want these conductors to be heating up beyond their insulation rating because that can cause insulation failure or damage. Ampacities for conductors 0 to 2000 volt must be per tables 310.15b16 through 19 and modified by tables 310.15b1 through 7. In other words, anytime we're sizing a conductor, so we have a load with a given ampacity, and we need to select a conductor that's big enough to carry that load, we're going to be referring to tables 310.15b16 through 19. And after we've selected that conductor, we could possibly have to modify those ampacities by tables 310.15b1 through 7, depending on the circumstance. So this is going to be the table that we use the majority of the time to select ampacity. This is table 310.15b16. So the way that we use this table is we have if you see it, first of all, you can see this table is broken down into a left and a right of copper and aluminum or copper-clad aluminum. Now above each of those, you can see that we have a 60 degrees Celsius, a 75 degrees Celsius, and a 90 degrees Celsius column. So what this means is that if we're using copper conductors, we have different ampacities for 60 degrees Celsius, different ampacities for 75 degrees Celsius, and different ampacities for 90 degrees Celsius. And the same thing if we're using aluminum or copper-clad aluminum conductors. So to use this table, the first thing we have to do is we have to identify if we're using copper or aluminum conductors. After that, we need to identify what temperature rating the conductors we're using are good for. And if you recall, in Module 1, back in Article 110, we talked about when we can use these different temperature ratings. Generally speaking, any circuit under 100 amps, we have to use 60 degrees Celsius. Any circuit over 100 amps, we can use 75 degrees Celsius. And then the only time that we could use the 90 degrees Celsius column would be if we're making an Ampacity adjustment. And even in that situation, the conductors can't be rated higher after the adjustment than what they're given in the 60 or the 75 degrees Celsius column. So once we've identified the material type as well as the temperature rating, then we just need to find the correct ampacity. So for example, if we were wanting to supply a load that was 30 amps with a copper conductor with an insulation rating of 60 degrees Celsius, what we would do is under the 60 degrees Celsius column, we would go down, and you have to keep in mind these values we see here are ampacities. So we see that a number 14 gauge conductor under our size AWG or KC mil column, we see a 14 gauge conductor is good for 20 amps at 60 degrees Celsius under the copper section. So our load being 35, we would need to be larger than that. So we would go down to a number 12, we see is only good for 25 amps. A number 10 is only good for 30 amps. And then finally we see a number 8 copper conductor at 60 degrees Celsius is good for up to 40 amps of current. Since our load is at 35, a number 10 is too small, so we would have to go to the next larger, which is a number 8, which is good for 40 amps. Another example of this would be if we were wanting to supply a load that was 200 amps using aluminum conductors at 75 degrees Celsius column. We would go to our aluminum or copper clad aluminum section under the 75 degrees Celsius column, and we would just go down until we find a conductor large enough for at least 200 amps. So if we keep going down, I see 180 amps for a 4-aught conductor, which would be too small, so I have to go to the next larger, which is 205 amps for a 250 kc mil conductor. So for our 200 amp circuit, using aluminum conductors at the 75 degrees Celsius that are rated for 75 degrees Celsius, I would have to use a 250 kc mil conductor. Moving on from there, we're going to be taking a look at our first ampacity adjustment situation, which is going to be caused by ambient temperature. Ampacity must be adjusted per table 310.15b2a or 2b when the ambient temperature is other than as shown in the ampacity table. So what it's talking about here is, you weren't able to see on our cutout there, if you're following along in your book, you'll see at the top of table 310.15b16, towards the end of the description of that, it tells you based on ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. So what this section here, 310.15b2, is telling us is that if we have an ambient temperature of something other than 86 degree Fahrenheit, we're going to have to adjust the ampacity of the conductors to account for that. Because obviously, if a number 10 gauge copper conductor is only good for 30 amps at 60 degrees Celsius, assuming that's in an 86 degree Fahrenheit ambient area, if we're installing those conductors in an area that's 110 degrees Fahrenheit, they're not going to be able to go up to 30 amps because that would cause the conductor to get too hot. And once again, that can lead to our insulation failure or damage. So we're going to be using table 310.15b2a when we're using our ampacity tables of 310.15b16 or 17, and then we're going to be using table 310.15b2b when we're using table 310.15b18 through 20. So depending on which table we go to determine our conductor's ampacity in the first place, that causes us to go to a different table in order to adjust that ampacity based on the ambient temperature. So we're going to take a look at 310.15b2a, since as I said, 90% of the time that you're selecting a conductor ampacity and 100% of the time that you're doing it for the sake of this course, you're going to be using table 310.15b16. So that would mean that you would be using table 310.15b2a for ambient temperature correction. So we can see at the top of this table, it tells us ambient temperature correction factors based on 30 degrees Celsius or 86 degrees Fahrenheit, which, as I said, 86 degrees Fahrenheit is what table 310.15b16 is based on. And at the top of this table, it tells us for ambient temperatures other than 86 degrees Fahrenheit, multiply the allowable ampacity specified in the ampacity tables by the appropriate correction factor shown below. So on the left-hand column here, we have ambient temperature in Celsius, and on the right-hand side, we have ambient temperature in Fahrenheit. And then we have temperature rating of the conductor, and we have our 60 degrees Celsius, 75 degrees Celsius, and our 90 degrees Celsius. So you can see, if we're looking at the Fahrenheit column, since most people in this course are probably more comfortable with Fahrenheit than Celsius, you notice that all the way up to our 78 to 86 degree Fahrenheit, our multipliers under our columns are actually you could think of as being positive. In other words, what this table is telling you is that if you have if you're installing an ambient temperature of less than 50 degrees Fahrenheit using the 75 degrees Celsius column, you can actually use 1.20 times the ampacity listed in the ampacity tables, 310.15b16, for the conductor from the table. Because under normal operating circumstances, that conductor's ambient temperature is actually going to be less than 86 degrees Fahrenheit, so you can actually let more current through the conductor. However, once we go above 86 degrees Fahrenheit, which would be hotter than we intend for the conductor to be operating at, we see that our values become what I would call a negative value. So at our very next point, 87 degrees Fahrenheit to 95 degrees Fahrenheit, we see that under the 75 degrees Celsius column, we have an adjustment of 0.94, which would be 94%. So if, once again, to reference our number 10 copper at 60 degrees Celsius, if we look at that same value here, that same row, this 0.91, we're essentially saying we can only put 91% of that 30 amps of current on that number 10. And that's to compensate for the hotter ambient temperature. So let's look at an example of how we would walk through doing this calculation. So we have a wire size for a given circuit determined to be a 4-aught AWG copper THHN using the 75 degrees Celsius rated insulation. In other words, we're using 4-aught copper THHN conductors using the 75 degrees Celsius column. And we see that these now since we're doing an adjustment, a key note to keep in mind is that we can actually use the ampacity listed in the 90 degrees Celsius column, assuming that once we do our adjustment, it does not exceed the value listed in the 75 degrees Celsius column. And this is an area where I see a lot of people make mistakes at. You have to remember you can always use that higher temperature rating, assuming the conductor is listed for that temperature rating, and assuming that your final ampacity doesn't exceed the original column value. So at our 4-gauge copper THHN at 90 degrees Celsius is good for 260 amps. Now the ambient temperature in the area we're installing is 47 degrees Fahrenheit, which is much higher than our 30 degrees Celsius, which we would normally want it to be at. So we reference table 310.15b2a, and we see that for 46 to 50 degrees Celsius, we have to do an 82% adjustment for 90 degrees Celsius insulation. So what this means is we take our 260 amps, multiply it by 82%, and we get 215.8 amps. And we note that this 215.8 amps does not exceed our 75 degrees Celsius ampacity, which for 4-aught copper at 75 degrees Celsius would be 230 amps. So this means that we can use our 4-aught copper THHN conductors for up to 215.8 amps of current when they're installed in this area where the ambient temperature is 47 degrees Celsius. Our next situation we're going to look at when we do an ampacity adjustment is for more than 3 current carrying conductors. And I'll explain a little bit more what I mean by this as we work through this slide. So if there are more than 3 current carrying conductors in a raceway or a cable, or if multi-conductor cables are not spaced, Table 310.15b3a applies. So in other words, if we take, for one situation we would say some EMT conduit, if we're going to install more than 3 current carrying conductors in that conduit, we have to make an ampacity adjustment. For our multi-conductor cable portion, if we're using a conductor that's, say, a 10-4 conductor, meaning it's 4 number 10 conductors in the same cable, once again, we would have to make an ampacity adjustment. And for our multi-conductor cable not spaced part, this would be referring to if we were installing conductors in a cable tray. If we're installing, say, once again, 10-3 conductors, even though each cable individually only has 3 current carrying conductors in it, if we're bundling a bunch of those together in a cable tray, we still have to treat that as being more than 3 current carrying conductors being together. Now the idea behind this is that if we have all these current carrying conductors bundled tightly together in the same area, whether it be inside a raceway or inside a cable, there's not going to be a lot of opportunity for heat dissipation. So there's not really going to be a way for that conductor to naturally vent and get rid of some of that heat. So thus we don't want the conductor to heat up as much in the first place to account for this. So for cable tray specifically, we have 392.80 applying, and I gave the example of when we would see that for a cable tray. Does not apply where raceway length is not more than 24 inches. This goes back to our idea of them being bundled. If we're only doing it for a short length, then the effect isn't really going to be considerable. And does not apply to AC or MC cable under certain conditions. So here's our table 310.15b3a, which is adjustment factors for more than 3 current carrying conductors. Now this table is a little bit more simple to use than our 310.15b2a. So all we do to use this table is on our left-hand column we have number of conductors. You'll notice it starts off with the lowest number being 4, because once again this is only when we're dealing with more than 3 current carrying conductors. So the first step we do is we determine how many conductors we have that are going to be installed in the same raceway. So let's say that we're installing 8 conductors in the same raceway or in the same multi-conductor cable. An important note there is that once again we're only talking about current carrying conductors. So grounding conductors don't count towards this. Grounded conductors do, since they carry current, but grounding or bonding conductors do not. So once again we're dealing with 8 current carrying conductors in the same raceway. So under our number of conductors we go down and we see 7 to 9, which is where 8 would fall. Then on our right hand column we see percent of values in table 310.15b16 through table 310.15b19 as adjusted for ambient temperature if necessary. So once again these are percentages under this column. So we see 80%, 70%, 50%, and so on. So for our 7 to 9, which is where we fall, we go across in that row and we see 70%. In other words, whatever the value listed in 310.15b16 is for the conductors we're using that are going to be bundled together in that same raceway, we can only put 70% of the ampacity listed in that table on that conductor. In other words, if the conductor is rated for 100 amps, we can only put 70 amps on that conductor. We have an example of that, of how we would actually do that calculation in a given situation. So in a given raceway, there are 6 number 2-aught AWG copper THHN and 5 number 6 AWG copper THWN current carrying conductors. So in total, we have 11 conductors, 6 of the 2-aught, 5 of the number 6. Now we see that 2-aught AWG copper THHN at 90 degrees Celsius is good for 195 amps. And we see number 6 AWG copper THWN at 75 degrees Celsius is good for 65 amps. And you may be wondering, why am I using the 75 degrees Celsius for the number 6s instead of the 90? And the reason for this is if we look at our insulation types, we can see, and we're looking at table 310.15b16, we can see that THHN is listed as an insulation type under the 90 degrees Celsius column. However, if we look at THWN, we see that insulation type listed in the 75 degrees Celsius column. In other words, THHN is good for up to 90 degrees Celsius, but THWN is only good for up to 75 degrees Celsius. So we can't use the 90 degrees Celsius column for our adjustment when we're using THWN. We can only go up to 75 degrees Celsius. So moving on, once again, the total number of current carrying conductors in the raceway is 11. We see that table 310.15b3, which was our adjustment table, for 10 to 20 conductors, we have a 50% adjustment. So for our 2-aught conductors, once again, they're good for up to 195 amps, times 50% equals 97.5 amps. And we note this does not exceed the 75 degrees Celsius rating for the conductors, since once again, our adjustment can't exceed the original value of the conductors for their normal temperature, which would be 75 degrees Celsius for 2-aught copper. For our number 6 conductors, we have 65 amps times 50% equals 32.5 amps. And we note this does not exceed the 60 degrees Celsius column, which would be the normal operating range for those conductors. Once again, anytime we're dealing with over 100 amps, we would be using the 75 degrees Celsius column. Anytime we're dealing with under 100 amps, we'd be using the 60 degrees Celsius column. So that concludes our adjustments that we're going to be taking a look at for across the board general adjustments. Now we have some specific adjustments for dwelling services and feeders. So for dwellings supplied by a 120 volt and 240 volt system, service and feeder conductors may be sized per 310.15b7 1 through 4. So under that specific circumstance, we have some additional adjustments that we have the option to make. You see the wording of may be size, so this is not a requirement. For services and feeders rated 100 to 400 amps, the conductors may be 83% of the load served. In other words, if we are going to install a service that's 200 amps, we can size the conductors to be 83% of that 200 amps. We don't have to size them for the full 200 amps. In no case is a feeder required to be larger than is specified in 310.15b7 1 or 2, which is what we just went over. Grounded conductors can be sized smaller than the ungrounded if certain requirements are met, which is 220.61 and 230.42 for services, and 215.2 and 220.61 for feeders. So we have some additional requirements for the grounded conductor where we can size them smaller. And once again, all these adjustments and options here are exactly that. They're options. These are not mandatory rules, they're permissive rules. Obviously, you can always size a conductor larger than it's required to be, but you have to size it to at least the minimum. So backing up a little bit from our adjustments and our opacity ratings, we're going to be taking a look at just conductors in general now, specifically with table 310.104a. Table 310.104a lists specifications for different conductor types, includes operating temperatures, abbreviation meanings, and usable locations. In other words, table 310.104a will tell you pretty much all the information you need to know about a given conductor type. Taking a look at an example part of the this table here, table 310.104a, we can see on the left-hand column we have the name of different insulation types, and under our type letter column we have what we would commonly refer to this as. This is where you would see your THHN, THWN, and so on. Under maximum operating temperature, this essentially tells you what the maximum value, the maximum temperature you can use that conductor at. So like we talked about before, our THWN conductors would show 75 degrees Celsius in this column. Our THHN conductors would list 90 degrees. Then we have some application provisions, which you can see some of the examples here. It specifies that it's usable in dry or dry and damp locations, or it could list that it's acceptable in wet locations. For insulation type, it actually tells you what the insulation is made of. So if we look down at silicone insulation type, we can see that its insulation is actually a silicone rubber. Then thickness of insulation. We have different information on the size of what the actual insulation is in terms of its thickness in both millimeters and mils. And then finally we have if the conductor has an outer covering. So some conductors may have something like a Simpool outer coating or something to that effect, and that'll be listed here in the outer covering. Sticking with conductors, we have our sizes and our different types. Table 310.106a lists the minimum size conductors allowed for different voltage ranges. Conductors number 8 AWG and larger must be stranded unless otherwise permitted or required. So once again, this is just some general information about conductors, nothing specific. We'll take a look at this table to give a better idea of what I mean. So table 310.106a, minimum size conductors. Once again, this is just a very general table. We can see that our conductor voltage rating in volts on the left-hand side, and we have a minimum size conductor AWG for both copper and aluminum. So if we're using conductors for a circuit that is 0 to 2000 volts, we can only use a minimum size of copper number 14 or aluminum number 12. If we're installing conductors for a 2001 volt circuit to a 5000 volt circuit, we have to use conductors minimum size 8 copper or 8 aluminum, and so on. So once again, this is just very general across all installations depending on what voltage you're installing at. And that's going to conclude this lecture. In our next session, we're going to be going over pull and junction boxes.